Hello everyone and welcome to the channel. In this video we'll take a look at interrupts on the 65816. We'll take a detour with some theory looking at what are interrupts, what are the kinds of interrupts that are available on this CPU. And then we'll do a live coding session where I will implement in assembly interrupt handling in our kernel. So I hope you enjoyed this video. Before we get started, I will put in the description box below two links to two amazing resources where you can learn about interrupts in much more detail. And that's the 6502 Interrupts Primer and the Investigating 65C816 Interrupts articles. Okay, back to the video. What is an interrupt? An interrupt is a way to respond to external events in real time. It will pause the currently running code to respond to that event. There are two categories of interrupts. Hardware interrupts are typically used with peripherals such as timers, clocks, handling video sync signals or user input. And the second category is software interrupts, which in the 6502, 65816 world are the break and the coprocessor instructions. Looking specifically at the 65C816 and its interrupt types, we can see we have 6 different types of interrupts. The first one is the reset interrupt. It behaves like an interrupt because it starts executing code from an interrupt vector, which we'll talk about later. But of course, the behavior is quite different because in this case, when reset is asserted, well, the CPU will reset and start again from the top of the program. So it's kind of a weird interrupt, if you want. The second one in the table is IRQ. That's a hardware interrupt, and that's going to be a normal priority external event. It's an interrupt that can be ignored by the user program, and you would typically use this one for all your hardware peripherals, your UART, your timers, etc. The NMI, which stands for non-maskable interrupt, is also a hardware interrupt, and this one is high priority, meaning it cannot be ignored by the user program, and it will always trigger an immediate response from the CPU. Usually it's a single source because NMIs are edge triggered and not level triggered, which is a small implementation detail, but it means that synchronizing multiple sources of NMIs is quite complicated. And you would typically use this to react quickly to maybe a vertical sync signal from your video circuit or to hook a debugger to the hardware, for example. The abort interrupt is a new interrupt in the 65816. It doesn't exist in the 6502. And that's a hardware interrupt that represents a memory access fault. It will, as its name implies, abort the current running instruction, meaning no register modification will occur. And it's an interrupt that is seldom used, and it's mostly useful to implement memory protection using a memory management unit, for example. If a program tries to access memory that it doesn't have the right to access, you would raise an abort interrupt and let the kernel figure out what it wants to do with the program. Then we have the break and coprocessor interrupts. Those are software interrupts and they each behave identically. The behavior behind them is user defined. You can do whatever you want with those software interrupts. Usually the break interrupt would invoke some kind of a debugger or machine language monitor, and the coprocessor interrupt would invoke a math coprocessor, or you could use it to build a kernel API. And both those interrupts are 2-byte instructions. They can have a signature, meaning a byte that is appended after the instruction, which could let you trigger different types of behavior depending on the signature byte. For example, if you use cop for kernel API, you would, for example, do cop signature 0 for the kernel API to print a string to the console, cop signature 1 for another kernel API function, etc., up to 255. So how does the CPU process an interrupt?
The first thing it does is finish the currently executing instruction, so an interrupt will not execute in the middle of an instruction, and that's the case except for abort, of course, where the instruction is aborted and no internal registers are changed. The second thing is it will push the processor state to the stack, so it will save the program counter, eventually with the program bank register if we're running in native mode, and that's to signify where to resume execution after executing the interrupt. And it will also push the processor status flags. That's going to be the carry flag, zero flag, and also the memory and index register size in native mode. So that's the minimal amount of information that the CPU needs to resume execution of the foreground program. Then once it has saved this information, it will jump to the location in memory pointed at by this specific interrupt's vector. So what is an interrupt vector? It's a 16-bit address of where to jump to handle the interrupt. The 656-816 has two sets of interrupt vectors depending on whether it's running in native mode or in 6502 emulation mode. So if you look at this table, on the right we have the 6502 emulation mode, and those vectors are identical to those of the 6502. And on the left we have the vectors when in native mode. And we can see, for example, if we're in native mode and we receive a non-maskable interrupt, the CPU will jump to the address that is stored at this memory location in the ROM. If it's an RAQ, then it will check this location in the ROM, etc. And there is a special case in 6502 emulation mode where RAQ and break are using the same interrupt vector, and it's the job of the interrupt handler to distinguish between the two. And of course, there is no reset vector in native mode because the CPU will always reset into emulation mode. So what's the job of the interrupt handler? The handler must happen as fast as possible to not disturb the running program too much and to be ready for another external event quickly. It also must be transparent, meaning the fact that an interrupt occurred must be invisible to the running program. The tasks of the interrupt handler are to save the state that is not preserved by the CPU itself. So that's going to be the CPU registers, A, X, and Y, as well as in native mode, the direct page and the databank registers. Then the handler has to respond to the external event, and that's going to be reading hardware device registers to figure out what happened and how to process an event. For example, did we get a character into our UART, or did a timer go off, that kind of thing. After it has responded to the event, it should restore the state that it saved in the first point. And that's because we want the handler to be transparent. So after exiting, the state of the CPU should be identical as before. And then it needs to return control to the program using the RTI instruction. All right, so this is it for the theoretical overview of how interrupt works on this CPU. Let's go into our editor and start writing code to handle interrupts. Alright, so I'm here in my editor, Visual Studio Code. I have my main assembly file open here, and then in my terminals I have here the Minicom connected to the BB816, and then on the right here is my Teensy monitor. So let's start implementing our interrupt handlers. In order to be able to iterate quicker, I will disable the memory checks in my post routine, because those do tend to take a lot of time on reset. And then let's start by taking a look at our interrupt vectors. For now, we have the reset vector set up here. Let's add placeholders for all the other types of interrupts. Okay, so these are placeholders for all the native mode vector locations. And then let's do the same for the emulation mode locations. There we go. Now, of course, if we run this code this way, we're going to have issues, because as soon as any of those interrupts happen on our hardware lines or in our software, the CPU is going to look at this address in order to figure out where to jump to. And if we set it to EA, then this doesn't point to anything in particular in memory, and so the behavior is going to be undefined. So we have to provide a pass-through location, and I will add it here. I will add a label that says interrupt return from interrupt, and this is going to be a single RTI instruction. This way we can replace all of the EAs here with our RTI location, and if we get any of those interrupts, the CPU is going to jump here, execute a return from interrupt, and then continue processing the code. So if you don't want to do anything with interrupts, you should at least have this in the code so that the CPU doesn't start executing unexpected code. Let's verify that everything still works. Let's compile. And yeah, it still works. Now let's try adding one source of interrupt, and I will look at how the break interrupt works because it's the easiest to set up in software. I will add my break instruction here, and we're going to have a break interrupt, and because we have set up our RTI here, nothing should happen and everything should still work. So let's try this. And yeah, everything seems to still be working. Now, I'm going to take a look at what happens in more detail by looking at the assembler report. We have our break instruction here at address 800E. Let's actually add a breakpoint in our TNC monitor so that we can watch what happens. And I know I haven't shown in the videos yet this functionality, B to set a breakpoint. Since this is not the main focus of this video, I'm going to start using it. Let's set a breakpoint at address 800E, start tracing, and reset. And here we have our breakpoint that has fired. And I'm now able to step through the execution of the code using the S key. So we see what the CPU does. And in order to execute the interrupt, we see that the microprocessor is saving the return address. So that's 0 for the bank address, and then 8010, which is right after the break instruction here. And then it's saving the processor status flag. This all goes to the stack. You can see it starts at the top of the stack here. That's address 01FF. And then it reads our interrupt vector here in native mode at address FFE 6 and 7. This is what we have set up here for break. And we know it points to our RTI, which is at 8140, which is what we get here. And then it jumps to 8140 RTI. We can see that's the right place. And then it will execute the return from interrupt, pop everything from the stack again, and then go to address 8010. But wait a minute, this is not the right address. It should go to 80F. And that's the first gotcha we have to keep in mind when using interrupts, and that is that break is actually a 2-byte instruction. It has what we call a signature byte, meaning you have to add a second byte here, and it can be anything. We'll just do 0, because the CPU, when it returns, is going to add 2 to this address here. And what happens now is that it has gone to 8010, which is actually the 0 byte in our load X instruction here. And so it thinks that this is an instruction and tries to execute it, but now it's getting out of step. And this is going to be an issue for the rest of the program. So now the question is, why is this still working then? Because if the program is getting out of step during the return from interrupt, then this shouldn't be working. And we can actually step through the program here and see that it actually executes a second break that comes from the 0 here in the loadx instruction, return from the interrupt again, and then it gets here to this one F, which it interprets as an RA with a long address. And it skips this branch here, goes to the push of X, and then to the GSR, and then the program continues. And it will most likely just print garbage to the serial console. And we are not seeing that currently because if we go to the configuration of Minicom, we can add hex display here by pressing S. And now if I reset, stop tracing, continue, we can see that we are receiving one F here, which is a non-printable character, and it doesn't appear in the display of Minicom. So we're thinking that it's working, but it's actually not. And we can also see in the LCD display that there's a space that has appeared, which shouldn't be there. So our program is not actually working. All right, so in order to simplify this, I will do a macro, and we can call this break. Okay, and so now in our program, we can just replace that with calling the macro. Let's try it out. We still have our breakpoint here, and now if we execute it, we see that the return address is still 8010, but now because we have the correct signature byte here, the program is shifted by 1, and so 8010 is now the correct return address. Okay, so now it seems that we're able to pass through a break interrupt. We can try the cup, and for cup, we do have to put in a signature byte in the assembly code itself. So I'm not sure exactly why break behaves this way in this assembler and why we have to use that macro. But for cup, we are forced to add a signature byte here. And yeah, we can see here the cup instruction. Let's try again. There we go. We have the cup. It's executing the interrupt, pushing everything to the stack, and then going to the address pointed to by FFE4 and FFE5, which is the cup handler. And then this points to our return from interrupt. That's great. And everything still works. Okay, so now let's try doing something a bit more complicated. I will add support for hardware interrupts. So let's remove our cup here. I'm going to do here a int native IRQ, and this is where we're going to handle our IRQ. So when the 65816 is executing in native mode, it can be configured to access memory as 8-bit data or 16-bit data. And the same thing goes for the index registers. So depending on the state of the M and X bits in the processor status register, the A register and the X and Y register could be either 8 bits or 16 bits. And so when we respond to an interrupt, we don't actually know what the code was doing at the time. We could potentially figure it out by reading the status register that has been pushed to the stack by the CPU. However, this will consume a few clock cycles, and actually the fastest way to handle this uncertainty is to assume everything was executing with 16 bits sizes. And if the code happened to be in 8 bits, then we will save an extra byte to the stack, but that's going to be faster on average than trying to figure out whether we should save 8 or 16 every time we have to handle an interrupt. So the first thing our interrupt handler has to do is switch to 16 bits indexes and memory. And then we want to save the registers that haven't been saved by the CPU itself. So in order to cover all cases, there are 5 registers we need to save manually. Those are going to be the data bank register, the direct page register, the A register, and then X and Y registers. And there we have saved everything that could potentially need saving. Of course, this is not the most optimized, because if you know that you are not going to change the data bank register or the direct page register, for example, you could skip those instructions and save a couple of clock cycles in your interrupt handler. But in order to future-proof this, I'm fine with spending a few extra cycles here. Then once we have saved the registers, I'm going to switch back to 8-bit registers, and that's because the rest of my kernel is written assuming 8-bit register sizes. Okay, and then in order to test this, I'll first do nothing here, and we can write the exit part of the IRQ handler. So how do we restore all this data? Well, we have to go back to 16-bit registers and then reverse this sequence here. So we need to pull Y, pull X, etc. And then we don't have to do anything with the registers bit here because the CPU, when executing our RTI here, will restore the original status register that the CPU had. So we don't need that. We just need to tell our assembler that the rest of this code should be assembled with 8-bit registers. And actually, I'll just add a comment here. All right, so this should be the basic interrupt handler that does nothing but save every needed register to the stack. Let's try executing it. So in order to test this, I will configure the ACIA to send interrupts when it receives a character, and then we'll easily be able to test interrupts just by entering characters here in our terminal. So this change is quite easy. We just have to go to the command register setting here, and instead of receiver IAQ disabled, let's just change this to enabled. And we also have to enable the interrupt on the CPU side by using CLI. This will enable IRQs. Okay, let's try assembling it. Everything still works. I'm going to add a breakpoint at the start of our interrupt handler routine, which is here, 8140. Let's start tracing. And if I type a character here, of course, this is not going to work because we haven't changed here our vector location. This is int native RAQ. Let's try again. Tracing, and if I type a character, yes. So we are currently here executing our native RAQ routine. We are switching to 16-bit registers, and then we will push everything to the stack. B, D, A, X, and Y. Then, of course, we go back to 8-bit registers for hypothetical kernel function here. Then when that's done, we go back to 16 bits and reverse the sequence and return from the interrupt. And we can see here that the code keeps executing. That's great. Okay, so I was tired of figuring out the exact syntax for the rep and sep instructions to change the index sizes. So I've written macros to do that. We have here a macro to change both sizes at the same time, and then only memory and accumulator, and then only the index registers. So I can now replace in my main assembly file this by plus mx 8 bits. And yeah, this is going to be much more readable. And in the interest of readability, I will also do the macro here, even though this sep instruction is not needed. Now that we have this here, let's add support for all the other types of interrupts. For example, we can have an NMI just by duplicating this exact sequence. We can handle the board again by duplicating this sequence. And you can see where this is going. This is a lot of duplication. So what I'll do is I will first separate out this sequence here into a macro. And I will call that int native entry. And it's just going to do this. And then we can call that for each type of interrupt at the beginning. And we can do the same for the exit. There we go. Now let's add the rest of the interrupts. There we go. And we have to remember to add them here as well. And I will keep the interrupt RTI here for the reserve locations. It's pretty unlikely that those are ever going to start being used, but I think it makes sense to have an RTI here anyway. Okay, so now that we have our handlers for native mode, let's do the handlers for emulation mode. So we can just copy everything here,
and rename native to emulation. And we do have to define our 2 new macros for entry and exits into emulation mode interrupts. So when we receive an interrupt in emulation mode, we don't have to worry at all about the register sizes. Neither do we have to worry about the databank register and the direct page register. So this can be simplified to just saving A, X, and Y, and that's it. Now we do have to set them here. And now there's a special case here because in emulation mode, RQ and break are shared. So we have to do some coding to separate the two. So in order to determine whether we're receiving an RQ or a break interrupt here, we have to look at the break flag on the CPU status register that was pushed to the stack by the interrupt. The CPU, before running its built-in status saving, will set the break flag in the CPU status register. And so we can just look at that. So in the 65816, it's quite easy because we can use the stack relative addressing mode to load from the stack at a certain offset. And the offset is going to be the location where we can find the status register after entering this handler here. In here, I will set up some offset addresses with the locations in the stack where the registers are saved. Now, the first thing that the CPU saves is the program counter. Then we have the status register. Then we save A, X, and Y. So the offset for these are going to be in reverse order, and those registers are 8 bits, so we have to add 1 each time to go back in the stack. So now in order to look at the status register from an interrupt, we can just use this offset here, and we can compare it to the CPU flag break. I don't actually have those constants defined, so let me do that now. Maybe here at the top, we can add all the CPU flags, starting with the carry, which is the first one, 0, IRQ disable, decimal mode, break, whether the indexes are 8 bits or the memory is 8-bit, and the overflow flag and the negative flag. And this one is only in emulation mode, and the sizes only exist in native mode. Alright, so now we can look at the break flag in our interrupt handler here. If it is set, then this is a break, so we can branch to handling the break interrupt. And if it's not, we just continue and we can handle the RQ here. Of course, when we're handling an RQ, we can just branch always to the exits. So let me add a comment to say what we're doing here. And actually, to follow the convention that we already have, we can add labels here and emu RQ and break. Okay, so now let's try it. So at the end of our initialization here, I will go back to emulation mode, and then we're going to be able to try with our same RQ from the ACIA whether we are actually reaching this point here. So I will set a breakpoint to the branch always instruction here. Let's program the code. Still printing hello world. So we can see that the emulation LED is still turned on. And if I print a character here, nothing happens. And yes, we are entering our interrupt entry point. Let's see what it does. So we push the registers. We look at the stack. So our offset is 4, and then this is offset 4 into the stack. The status register is 22. And if we're set, we're going to now branch and reach our branch always here. Great, so we have successfully separated the RQ. Now let's try with a break. So instead of wait and stop here, I will just do break the macro. And if we reset, that's going to be too slow. I guess I just have to wait for this to go through, and I'll cut it in editing. Actually, let's move this higher up. So here, for example. Okay, reset, and yeah, we are reaching our breakpoint. Now let's see what it does. So the registers, look at the stack. Do we branch? Yes, we do branch. So it works. Perfect. All right. We have successfully implemented emulation mode IRQs. Okay, so now the next thing I want to do is I want to provide a way for user programs to hook into the interrupts. So for now, all the handlers that we have here are hard-coded into the ROM. And if we end up loading a program to RAM, for example, through the serial link, it would be nice if that program could add its own interrupt handling. Let's say you're building a game, you want the program to be able to hook into the interrupts to handle button presses, for example. So in order to do that, we need to have a location in memory where the user program can hook into the interrupts. The way it will work is the kernel is going to define those hooks with some default value that will do nothing. And then if a user program wants to use a given interrupt, it needs to put into the hook location the address of a function it wants to be executed. And it must take care to also save and return to the default kernel location. So let's do that now. So at the top of my program here, I'm going to set up a number of locations. And I will put those locations in the 0 page. That way it's fast to access. And we're going to have one for each mode and each type of interrupt. And each of those locations will store a memory address. So they're each going to be 2 bytes, which means we have to increment the value by 2 each time. Okay, what will happen is for each interrupt handler that we have here, it will do the entry and then it will jump to the address pointed to by that vector. And by default, we can set up the kernel so that the default location of this address actually points to the exit of the interrupt, and this way we can simplify the code a bit. So if I actually remove this macro and make it just a label, same thing for the native one, we can remove all the calls to this macro here, and we can also remove this branch. And then all we have to do is make sure that this location is set up with the exit for the interrupt. And so in our kernel initialization code, before we enable the interrupts, we're going to initialize the interrupt vector. For this, we'll switch to 16 bits mode because we're working with addresses. We're going to load the address of our exit into the A register. And we're going to store it to all the locations here. And then we're going to do the same for the emulation mode exit and go back to 8 bits memory. So now when an interrupt happens, let's say we get an IRQ, the CPU will jump to the location pointed at by this label, int native IRQ at address FFFE and FFEF. This label is here. It's going to execute the entry point for native interrupt, and that's going to be saving all the registers in 16 bits mode. Then it's going to look at this memory location in 0 page. And because for now we're not doing anything with that, this location in 0 page from our initialization is going to point to the native exit. And the native exit is here. And that's just going to restore everything and return from the interrupt. So this shouldn't change any behavior in our kernel. It's just a way for user programs to easily hook into those locations. All right, so now the question is, how could we use this? So in order to show this, I'm going to simulate a user program. And let's say this is going to be the user program that we want to run. It's going to print hello world and then wait for characters sent to the terminal. So let me actually move this to a separate file so we can see easier what's the program and what's the kernel. And let's say we want to handle interrupts from the ACIA. So the first thing we have to do before enabling interrupts is to switch the memory to 16 bits mode, to get the address pointed to by the native RQ vector, and to save this in a location that is specific to our program. And we're going to make that 14 because that's where we have space in our 0 page. So we will save this default location, and then I will write an interrupt handler here. And so we want to load the address of this label here, and then we're going to store it the RQ vector, and then we can switch back to 8 bits. So with this, we can save the existing RQ handler and we add our own. And then in our own handler, we're going to do something here. And when it's finished, we want to jump back to the address that we saved. This way, the kernel can still do its own processing and then exit from the interrupt. So let's say we have an interrupt from the ACIA. We're going to get the character, print it to the console, and then exit from the RQ. And so because we have removed the loop, this is going to continue executing here. So what we'll do is we're just going to waste some cycles and stay in this loop here. So this should be the way to implement a user program that uses our RQ vectors. So let's try this now. Let's assemble it. Okay, so now we can see that the CPU is waiting for the interrupt. Let's try typing something. And yeah, it works. So we are successfully processing interrupts from the ACIA now. Great. All right, so I think I will end the video here. I'm pretty happy with the results and the structure we've been able to put in place to make use of interrupts on this computer. It's going to make it much more easy to implement a feature-complete and performant serial communication driver for the ACIA in the future. So I hope you enjoyed this one. If you have any questions or feedback, please let me know in the comment section. If you'd like to support this project and help me with the purchase of tools and parts necessary to make this computer a reality, you can support me on Patreon. I will put the link in the description box below. And in any case, I hope to see you in the next video. Goodbye.